Okay, so today we're jumping right into a big one. The paper is Latent Forcing, Reordering the Diffusion Trajectory for Pixel Space Image Generation.
Yeah, this one's been making some waves. It's by Alan Bade, Eric Ryan Chan, and a team from Stanford and the University of Michigan.
And it proposes this new method, latent forcing, which, tries to get the best of both worlds.
Exactly. It's trying to reconcile the efficiency we get from latent diffusion models, think stable diffusion, with the, let's call it the purity and precision of pixel space diffusion.
And the core idea is really clever. Instead of making this binary choice, do we use a compressed latent space or this huge pixel space, they just do both.
Both at the same time in a single model. But the real aha moment, the trick, is that they use separate time schedules for the latents and the pixels.
So they force the model to denoise the high-level stuff first.
Right. They use DINOv2 features as the latents, and they make the model figure those out before it starts worrying about the pixels. So the latents become this kind of scratchpad, a guide.
And the results speak for themselves. It hits state-of-the-art for diffusion transformers generating in pixel space on ImageNet.
It blows past the previous CHAM, just-in-time, or GT diffusion, and it does it without the information loss you normally get from a standard tokenizer. It really changes how you think about generation.
Okay, that's the quick summary. But for everyone still with us, let's really dig in. To get why latent forcing is such a big deal, we have to talk about the civil war that's been happening in generative models.
It's a good way to put it. You really have two main camps.
On one side, you've got latent diffusion models, LDMs. This is what everyone knows, right? Stable diffusion, Midjourney. They all live here.
Right. And they work by taking an image, and instead of looking at the pixels, they use a tokenizer, usually a VAE, a variational autoencoder, to squash it down.
Into a much smaller, more manageable latent space.
Which is great for speed. It converges faster, uses less memory, and the quality is obviously very high.
But there's a catch.
There's a big catch that people tend to ignore. It is not an end-to-end system. That tokenizer, the VAE, it's lossy. It has to throw information away to compress the image.
And that's where you get weird artifacts, right? The classic six-fingered hands or garbled text from older models.
Exactly. The high-frequency details just get mangled in the compression. The tokenizer just doesn't have the bandwidth for it.
Okay, so that's camp one. Then on the other side of the battlefield, you have the purists.
The pixel diffusion camp. They work directly on the raw image pixels. No compression, no VAE, no information loss. It's end-to-end in the truest sense.
So if it's so pure, why isn't everyone using it? Why did latent diffusion basically win round one?
Because it's just insanely expensive computationally. An image is a massive high-dimensional object compared to a little latent vector.
And the model has to learn everything at once.
Everything. It's trying to figure out high-frequency details like, the texture of a brick wall. At the exact same time, it's trying to learn low-frequency structure like this is a house.
It's like trying to paint a masterpiece while you're still mixing the pigments from scratch for every single brushstroke.
That's a perfect analogy. It's incredibly inefficient. So you've always had this trade-off. Fast and a bit lossy, or perfect and impossibly slow.
And this paper comes along and says you're asking the wrong question. The problem isn't the space latent versus pixel.
It's the order of generation.
Which makes intuitive sense. When a person draws, you don't start by perfectly rendering a single eyelash in the corner.
No, of course not. You sketch the overall shape, you block out the major forms, you create a storyboard, high-level structure comes first, then you fill in the details.
And pixel diffusion fails because it doesn't do that. It treats the eyelash and the face shape as equally important from step one.
Latent forcing basically tells the model, hey, let's build the scaffold first, then we'll worry about the paint job.
Okay, so let's get into the nuts and bolts of how they build that scaffold. Because when I read that they feed in raw pixels and latent embeddings at the same time, my first thought was, isn't that just making the input even bigger?
It seems totally counterintuitive, yeah.
If pixel space is already too expensive, how does adding more data on top of it help?
So architecturally, it's built on a standard diffusion transformer, a DIT. Nothing too crazy there. They take an image, they patchify it into 16 by 16 squares. Standard stuff.
Okay.
But then for each of those patches, they also run a pre-trained encoder, in this case, DINOv2, to get a rich semantic feature vector.
So for a single patch, I have the raw pixels that might just look like, say, a bit of brown fur.
Right. And you also have a DINOv2 vector that essentially says this is semantically related to dog ear.
And it gets both of these at the same time.
It gets both. They're tokenized and fed into the transformer sequence. The key is that the model sees this composite view. It's one model processing two parallel streams of information about the same patch of the image.
Is that a big architectural change? Does it add a ton of parameters?
Almost none. It's about a 0.5% increase in parameters over a standard DIT. It's a tiny change, mostly for an extra time embedding.
Wait, I have to push back on this efficiency thing. You're telling me I have to run a whole separate giant encoder DINOv2 on top of the diffusion model. How is that not just doubling the compute?
That's a really common and fair question, but you have to remember the scales here. Yes, you run DINOv2, but it's a VT large. It runs once per image up front.
Right.
The diffusion model, DIT, is an iterative process. It might run for 50, 100, even 200 steps. That's where the real computational cost is. The forcing makes that iterative process converge so much faster and to a higher quality that the one-time cost of running Dino is. It's basically a rounding error.
Ah, I see. So the cost of hiring the architect is cheap compared to the cost of having the construction crew wander around aimlessly for weeks.
That's it, exactly.
You mentioned an extra time embedding. This seems to be the real magic here. It's not just about the dual inputs, but when the model pays attention to them.
This is the multi-time scheduling. The model actually has two time variables it tracks, t-pixel and t-latent. In training, they're sampled independently, so the model learns to denoise both at any given time.
But at inference, when you're actually making an image, you control the schedule.
You control it, and the schedule is latents first. You force the model to denoise the DINOv2 features on an accelerated timeline. They become this intermediate computation, this scratchpad.
The model figures out there's a car here, a building there, using the latents.
Once that structure is clear in the latent space, that information then conditions the generation of the high-frequency pixel details.
And after all that, what happens to the scratchpad?
You just throw it away. At the end of the denoising process, the latent tokens are simply discarded. The output is just the raw, beautiful pixels. No separate decoder, no GN needed to clean it up. It's really elegant.
I really like your scaffolding analogy. In a normal LDM, the scaffolding, that compressed latent, is still part of the final building. You have to patch it up and pretend it's not there.
Right, you're stuck with it.
Here, it's true scaffolding.
Yeah.
You build the structure, then you remove the guide, and the final image stands on its own.
And because it's temporary, it doesn't matter if the scaffolding itself isn't perfect, as long as it guided the pixels into the right place.
Let's get into the theory for a second, because the paper talks about signal-to-noise ratio, SNR, and why this order is so fundamental.
Yeah, they make the argument that generation order is really just another way of talking about the trajectory of the SNR for different types of information. They even show mathematically that scaling the variance of a data type, like the latents, is equivalent to just shifting its noise schedule.
Which is a very technical way of saying what?
It's a technical way of proving that figuring out the easy stuff, the what, the semantics, first makes figuring out the hard stuff, the how, the pixels, way, way easier. The experiments confirmed it.
This sounds a bit like another technique we've seen, REPA, or representation alignment, that also uses pre-trained features. How is this different?
That's a crucial distinction. REPA is a distillation method. It tries to bake the knowledge from something like DINOv2 directly into the model's weights during training.
So it's trying to make the student model think like the teacher model.
Exactly. But latent forcing is different. It's not trying to change the student's brain. It's just handing the student a cheat sheet during the test. And unlike REPA, latent forcing is completely lossless at inference time because it's using the raw pixels in the end.
Okay, the theory holds up. But let's talk results. Does it actually win?
It absolutely does. On ImageNet, it sets a new state-of-the-art for pixel diffusion transformers at its compute scale.
And it's going up against GT, just-in-time diffusion, which was the reigning champ in pixel space.
And it didn't just win, it was a knockout. We're talking about FID scores where lower is better. In this field, getting a 10% drop is a big deal.
And latent forcing got
a 2.5x reduction in unguided FID compared to GT. That's not an incremental improvement, that's a generational leap. Even against GT boosted with REPA, latent forcing still got a 1.9x reduction.
That's incredible. And they found the best way to do this was the cascaded schedule.
Yes. The best results came from a schedule where you denoise the latents almost all the way, and then you start denoising the pixels. It's a clean handoff from planning to execution.
But you don't strictly have to do that.
No, even joint denoising, where the schedules overlap, works very well, as long as the latents stay significantly ahead of the pixels in their denoising process.
The ablation studies were my favorite part. They really tried to break it. What happened when they reversed the order and forced pixels first?
Performance completely cratered. It just falls apart. The model gets bogged down in structural uncertainty. It's trying to paint the bricks before it even knows where the wall is supposed to go.
But the real shocker for me was when they swapped out the encoder. They took out the super smart DINOv2 and put in DINOv2
Which is a much, much weaker model. Trained for only 150 epochs, it barely knows anything compared to DINOv2.
And the result?
It still massively outperformed pure pixel diffusion.
Get out. So it's not just about having a genius teacher whispering the answers.
This is the craziest part. Even with a weak learner as the guide, the structured plan then execute process is so fundamentally better that it still beats the state of the art. It proves the magic isn't the guide itself, it's the process. It's the scaffolding.
So even a bad map is better than no map at all.
A bad map gets you way closer than just wandering in circles. The structure is more important than the intelligence of the guide.
They also tried it without class labels, right? Unconditional generation.
And it worked great, which tells you this ordering benefit is fundamental to the generative process. It's not just a clever trick for using class labels. The model learns to create its own internal plan.
Yeah, this all sounds amazing, but let's get practical. For the people listening who might want to implement this, where are the hidden landmines? Usually these dual stream things are a nightmare to drain.
There are a few key details. First is the prediction target. They use X prediction with V-loss weighting, following what GT and Simple Diffusion did.
So they're not predicting epsilon, the noise, which used to be the standard. Why not?
Predicting noise is fine in a smooth, low-dimensional latent space. In pixel space, it's chaos. It's high variance and unstable. Predicting X, the clean image, or V, a velocity term, gives you a much more stable training signal.
Got it. Predict the image, not the static.
Mm-hmm.
What about guidance? Everyone loves CFG, classifier-free guidance.
Interestingly, they've found that auto-guidance, another method from Karas and team, works best here.
Why is that?
The DINOv2 features are already so rich with class information, they're already guiding the model towards the right semantics. So adding standard CFG on top is kind of redundant, especially during the pixel rendering phase.
What if you had to use CFG?
The best results come from applying it only to the latent time steps. Guide the plan, not the execution. Once the plan is set, let the renderer just follow it.
There's one more thing here that I think just completely flips conventional wisdom. We always think about compression. Smaller is better. We compress 32x, 64x.
Right, compression is king. That's been the mantra.
But latent forcing uses an input space that's actually bigger than the raw pixels.
It is. You have the pixels and you have the latent vectors. It works out to about 6 floating point numbers per pixel of input data. It's the least compressed input space to ever get SOTA on ImageNet 256.
So let me get this straight. We're using more data, not less, and getting better, more efficient generation.
Exactly. We're using more data, but we're organizing the processing of that data over time. The counterintuitive takeaway is that you don't actually need to lose information to make generation tractable. You just need to sequence it correctly. Compression was a crutch we used because we didn't know how to manage the timeline.
Wow. We were optimizing for space when we should have been optimizing for time.
That's the paradigm shift. We thought the bottleneck was the size of the data. The real bottleneck was the order of revelation.
Okay, let's zoom out. What does this mean for the future of generative models?
I think it fundamentally challenges the need for separate, frozen, lossy tokenizers. The whole pipeline for the last few years has been train a VAE, freeze it, then train a diffusion model on its outputs.
And latent forcing says, Mike.
It points to a future where the tokenizer isn't a separate black box. It's an active, dynamic part of the generation process itself. It becomes a temporal guide, not a static compressor. The line between the compressor and the generator just dissolves.
It feels like we're moving towards a single, more elegant end-to-end system instead of bolting all these different pieces together.
And it's a system that feels more aligned with how we actually perceive the world. We see the big shapes first, then the details. We don't see some compressed code and then decode it.
That brings up a final thought for me. If order matters more than compression, what about other modalities? What about video?
Now that is the really exciting, provocative question, isn't it? Video models today struggle so much with long-term consistency.
Right.
So imagine instead of trying to generate a whole movie as a tiny latent cube, or generating frames one by one and hoping they connect, what if you could force a video model to generate plot points or story beats as latents first?
You generate the entire storyboard of the scene in the latent space.
And then use that storyboard to condition the pixel-by-pixel generation of the individual frames. This paper suggests that treating time as this flexible multi-stream dimension could be the key to unlocking true high-fidelity pixel space generation for everything.
It makes so much sense. You wouldn't shoot a movie without a script. Why are we asking our AI models to?
Structure first, details later. It's a simple idea, but it looks like it could be the key to the next generation of models.
This paper, Latent Forcing, really feels like one we're going to look back on as a moment where we realized we were making things much harder on ourselves than we needed to.
Sometimes the most complex problems just need you to put things in the right order.
A perfect way to end it.
Yeah.
Well, that's all the time we have. Thanks for this fantastic deep dive.
Always pleasure.
And for everyone listening, definitely check out the paper from Bays and Chan. It's well worth the read. We'll see you next time.